Questions 21 through 25 on the 2020 Grade 9 Pascal Math Contest. In the 4x5 grid shown, 6 of the 1x1 squares are not intersected by either diagonal. When the two diagonals of an 8x10 grid are drawn, how many of the 1x1 squares are not intersected by either diagonal? In the first one, let's look at which 6. This one, these two, and this one. Those 6 are not intersected by the diagonals. Now, they are then giving us a much bigger one, and they're saying, okay, we've talked about the 4x5, but now we want to look at an 8x10. Well, what's interesting about an 8x10 is it's exactly 4 times the one that they gave originally. So approximately like that. If it's 8x10 in full, 8x10, then each of these would be 5x4. So we really can just look at this 5x4 and then multiply the answer by 4, since this is just 4 of those. But the difference is that now we're looking at diagonals for the whole. So we're looking at diagonals that go all the way across the entire one. So that would be the equivalent, really, of just looking at a diagonal like that. So only one diagonal, and then counting how many squares does it touch and not touch. Well, it touches 1, 2, 3, 4, 5, 6, 7, and 8. So crosses or touches, whichever term you want to use, crosses 8. So it does not cross 12. So if it does not cross 12, then it does not cross 12 here, does not cross 12 here, here, and here. This rectangle, this rectangle, this rectangle, this rectangle. So in total, it would not cross 4 times 12, which is 48 of these tiny squares. So number 21, the answer is D. In the diagram, PQ is a diameter of the larger circle. Point R is on PQ, and smaller semicircles with diameters PR and QR are drawn. If PR is equal to 6 and QR equals 4, what is the ratio of the area of the shaded region to the area of the unshaded region? PR is 6 and QR is 4, so that means PQ all the way would be 6 plus 4, which is 10. So we have to figure out the area of the shaded region divided by the area of the unshaded region. Okay, so first let's figure out the total area of the entire circle. So that's going to be pi r squared for big R. And the big R, well, the big diameter is 10, so the big R must be 5. So 25 pi is the area of the full big circle, this whole thing. Now, let's figure out what is the area of the shaded region. The area of the shaded region, to me, looks like, first, this small circle, half of it, so pi small r squared divided by 2. Then this semicircle, subtract that semicircle. So pi big R squared divided by 2 plus pi, I guess, intermediate or middle, the middle value, squared divided by 2. And remember that we've got to subtract that. Okay, let's plug in our values for the radius for each of these. So this is going to be pi times QR is 4, so the radius is 2. So 2 squared divided by 2. The big R was 5. And the middle R, meaning the radius of that, if PR is 3, then that means the radius, PR is 6, so the radius is 3. So 3 squared divided by 2. So this looks like 2 pi plus 25 pi over 2 minus 9 pi over 2. So that is 2 pi plus 16 pi over 2, and that is 2 pi plus 8 pi, which is 10 pi. So the area of the shaded region is 10 pi. Area of the unshaded region would basically be the total area, which is 25 pi, minus the area of the shaded region, which is 10 pi. So that would be 15 pi. So it would be over 15 pi. And when you cancel out the pi's, you just get 10 over 15. And 10 over 15 in lowest terms is 2 over 3. Therefore, number 22, the answer is B. Ali, B, Shay, Deb compete in a checkers tournament. Each player plays each other player exactly once. At the end of each game, either the two players tie or one player wins and the other player loses. A player earns 5 points for a win, 0 points for a loss, and 2 points for a tie. Exactly how many of the final point distributions is possible? Let's go through these one at a time. Well, if Ali has 15 points, then that means he's won all three. So he has 3 wins. Now, each of those wins has a loss associated with it. So that means that B, Shay, and Deb each have 1 loss. Okay. Now, we've taken care of Ali. Now, B, C, and D, these players have been accounted for one of their games. They were all 3 losses because we had to match the 3 wins with 3 losses. Okay, now each of those has 2 games remaining. So we've taken care of this 15. Now, how does somebody get 7 points? The only way to get 7 is to have 1 win and 1 tie. It's the only way. Now, if there's a win there, then there's got to be a loss somewhere else to match it, right? So I'm going to put that loss over here with D. So that would work. Now, there's a tie here, so that means the tie has to go somewhere else to match, correct? So I'm going to put the tie here, 1 tie. And then now we still have 1 final game for C and D. And so far, D does not have any points. 1 loss, 1 loss, 2 losses. But Deb's point total is 2, and that can only be obtained with 1 tie. So that means we have to put a 1 tie here, because if one team ties, there has to be another tie with another team. Let's see if these point totals add up. 1 loss and 2 ties is 4 points. 2 losses and 1 tie is 2 points, so this is possible. Great. So put a check mark there. Now let's talk about the next one. Again, A, B, C, D, and off we go. So here we have 10, 10. The only way you can get 10s is with 2 wins. So we got 2W here and 2W here. Now, those 4 wins total have to be matched by 4 losses somewhere, correct? So we've got to put 4 losses somewhere. Well, I'm going to put 1 loss here, 1 loss here, and then 1 loss here and 1 loss here. So we have taken care of A and B. Their 3 games have been accounted for. That's done. Now we have to find a way to give Shay and Deb 4 points. We have to still talk about 2 games each. Now let's say C and D played each other and they tied. Okay, that's great. That would each give them 2 points. But then what's their 3rd game? Well, their 3rd game had to be accounted for by these losses. If there was a loss here and a loss here, they have to put in 2 wins somewhere. So there had to be a win here and a win here. And now look at the point total. That's actually 7 and 7. And that doesn't match our 4 and 4. So when you, in a very similar way, fiddle around with this, you'll find that this is not possible. Okay, let's try the next one, A, B, and C, D. So again, we have Ali with 15. So that means he got 3 wins. And we have to match out the wins with losses. 3 wins, there has to be 3 losses somewhere. So that takes care of A. Now B has 5 points. Now the only way to get 5 points is by getting a win. So there has to be a win here. And similarly, Shay has 5, so there has to be a win there. Okay, now 2 wins, there has to be 2 losses somewhere. Can't put them here. He's already got 3 games. He's done. Where can I put the losses? Well, a loss has to go here. And we'll put loss here. Now I've got to figure out how to get Deb 2 points. The only way she can get 2 points is with a tie. And if she ties somebody, there has to be a tie somewhere else. So the only spot left is here. Okay, well, let's check out the points now. LWL, that does make 5 points. LLT, that gives you 2. But LWT, that gives me 7. So unfortunately, that doesn't match this. So that's wrong. And finally, we got ABCD, the last one. So Ali now has 12 points, so that means he got 2 wins and 1 tie. That's the only way to get 12. If there's 2 wins, then that means there was some losses somewhere. So I'll put the loss here, 1 loss here, and 1 loss here. Okay, now there's a tie here that Ali got. He had to have tied with somebody else, so I have to put a tie somewhere else. If I put a tie here, that would make D have 2 points, but D has 0, so I can't put the tie there. If I put the tie here, that would mean 2 points, but then 5 in total. That would mean an additional 3 has to come from something. There's no way to get 3 points. You can get 2 points, but you can't get 3. You can get 4 points, but there's no way to get 3 points. Okay, so it doesn't go there. If I put T here, okay, that's 2 points, but then from those 10, if those 2 are counted by the tie, then there's a remaining 8. There's no way to get 8 points in 2 games, no matter what you try. So this doesn't work, and therefore this is also no good. So of those 4, the only one that's possible is the first one. Therefore, number 23, the answer is B. Lucas chooses 1, 2, or 3 different numbers from the list 2, 5, 7, 12, 19, 31, 50, and 81, and writes down the sum of these numbers. If Lucas chooses one number only, this number is the sum. How many different sums less than or equal to 100 are possible? We have a list of 8 numbers. So if there's only one number, then from those 8, you just choose 1, and that's 8. So 8 is the start of the different sums, and the sums are right there. Those sums, of course, would be 2, 5, 7, 12, 19, 31, 50, and 81. Okay, that one is easy. What if you choose 2 numbers? Then from those 8, you have to choose 2. 8 choose 2 is 28. But we have to account for the fact that there could be some doubles, and there could be some that are greater than 100. We want less than or equal to 100. Okay, so the ones where there's 2, it wouldn't take that long to figure it out. So we got 2 and 5, right, which is 7. 2 and 7, which is 9. And then 2 and 12, which is 14. 2 and 19, 21. 2 and 31, 33. 2 and 50, 52. And 2 and 81, 83. And in a very similar way, 5 and 7, which is 12. I'll just write them all out. I don't think you need me to voice them all out. So I'll just make the list. And then now we get to the one where we're combining the 7 and the ones. So 7 and 12, 19, and so on. 26, 38, 57, and 88. And then now we use the 12 to combine them. So 12 and 19, that's 31, and 43, 62, 93. And then 19 plus 31, that is 50, and then 69, and then 100. And then we're up to now 50, or 31, I should say. 31 and 50 is 81. And then we have a 112, and then finally 50 and 81 is 131. Okay, so this is the list. When we have 2, this is the full list, and it should be 28. Now what we have to do is eliminate the ones that are greater than 100, because that's not less than or equal to 100. And it looks like there's only 2 of those that we eliminate. Now we have to get rid of any doubles, any number that has already appeared, because we want different sums. We want unique sums. How many different sums less than? or equal to 100. So if it's counted twice, we don't want that. Well, the 7 has already appeared here. Let's see what else. The 12 already appears here. The 19 already appeared. The 31 already appeared. The 50 appeared. And the 81 appeared. So these ones we have to get rid of. So 1, 2, 3, 4, 5, 6, 7, 8. So from that 28, we have to subtract 8. So therefore, we have 20. 8 and 20. So far, those are the unique sums. Now, we have to do the same thing this time for 3. Now, for 3, it will seem quite time-consuming, and it is. But the good news about this question is that there's a shortcut. We have 3 numbers now. Well, 3 numbers is 8 choose 3. 8 choose 3 is actually 56, so that's a pretty big number. Quite a few combinations. But the good news is, due to the nature of this list, any sums that involve consecutive numbers will end up as a repeat. So let me give you an example of what I mean. Let's say I said I want 3 numbers, and I'm going to choose 5, 2, and 7. Right? Those are all consecutive. And I add those up, and the sum would be 14. Well, 14 is already included. So that would not give me a unique sum. Okay, let's try 2, 5, and let's go a little bit farther down. 31. 2, 5, and 31, that's 38. And 38 is already included. Okay, let me get away from this 2 and 5. Let's see if I can do this. Keeping in mind that I guess the undesirable way of doing it is having consecutive. So let's see what happens if I choose consecutive again. 12, 19, and 30. Let's choose 50. 12, 19, and 50 is 69 plus 12, which is 81. 81's already there. So I hope you can see that having consecutive numbers will result in giving you something that's already been created. So the rule is that we're going to choose 3 numbers that are not consecutive in order to get unique sums, unique new sums. So to repeat, due to the nature of this list, any new sum must come from 3 numbers, no 2 of which are consecutive. And if we do that, it considerably kind of reduces our time, because this is a time-consuming question. So instead of 2, 5, those are consecutive, so I got to jump at least to 7. And then after 7, I can't choose 12, I have to choose 19. So that's how I'm going to make my life. So 2, 7, 31, 2, 7, 50, 2, 7, 81. And then very similarly, 2, 12, 31, 2, 12, 50, 2, 12, 81. And then 2, what's the next one? 19, 50, 2, 19, and 81. Okay, we've exhausted the 2s. Let's move up to the 5s. So we got 5, can't choose 7, 12, can't choose 19, 31. See how I'm doing it? I can't choose 2 consecutive numbers, because if I did, it would give me a number that it would give me a sum that I've already obtained. So 5, 12, 81. And then now let's move up to the 19, 5, 19, 50, 5, 19, 81. Okay, I've exhausted the 5s, and I'm up to the 7s now. 7, 19, 50, 7, 19, and 81. And then I'm done with that. Now I'm up to 12, 12, 31, and 81. And I think that's it. That's the end of the road. Okay, that's good. So I didn't have to do 56. I only had to do whatever this is, probably about 15 or so, 16 maybe, whatever it was. Okay, now let's figure out the sums. So this will be 28, 40, 59, 90, 45, 64, 95, 71, and 102. 48, 67, 98, 74, 105, 76, 107. And this is 124. Okay, so first let's eliminate the guys that are greater than 100 because that's outside our range. And then now we have to look, are there any doubles? And there will not be. I don't need to even worry about looking at this list and trying to see are there any doubles because I did not choose any two that are consecutive. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, this one's also greater than 100. So don't include that one. So you just got to be a little careful. So that's 13. All right. So I have 8 up here, 20 here, and 13 here. So my total 8 plus 20 plus 13, and that is 41. 41 is the answer to number 24. That would be E. We call the pair mn of positive integers a happy pair if the greatest common divisor of m and n is a perfect square. For example, 20 and 24 is a happy pair because the greatest common divisor of 20 and 24 is 4. Suppose that k is a positive integer such that 205, 800, and 35k is a happy pair. The number of possible values of k with k less than or equal to 2940 is. Before we begin, let's do a little bit of a primer about GCD, greatest common divisor. So the motto of this question will be think minimum. And it will be clear later in the question as to why this is the motto. So let me explain. Let's say I gave you two numbers and I said find the GCD. But I'm going to make them some big numbers. The very first thing you want to do is break them up into its prime factors. So for example, this is not broken up into its prime factors. So eventually we will need to do that. But let's just give an example, something different. So 2 to the power of 7, 3 to the power of 2, 5 to the power of 4, 7 to the power of 1. And we'll stick in another one, 11 to the power of 3. And then I've got to create another number, right? So 3 to the power of 5, 5 to the power of 1, 7 to the power of 4, 11 to the power of 2, and I'll put in another 13 to the power of 1. And I said find the GCD. How do you do that? Well, the GCD will be equal to as follows. For 2, it will be the minimum of the powers of 2 from each of these. So here it's 7. Here there is no 2. You notice there's no 2 to the power of something. So that means it's really 2 to the power of 0. So that's basically what you put there. Then it would be 3 to the power of the minimum of the powers. So 2 here and 5 there. So 2 and 5. And then next one, 5 to the power of the minimum of 4 and 1. So 4 and 1. And you're getting the hang of this, hopefully. And then keep multiplying. So the next one will be 7 minimum, 1 and 4, right? Next one, 11, the minimum, and those exponents are 3 and 2 this time. And then finally 13 and the minimum. Well, here there is no 13. So it's really 0 there, but there's a 1 over here. Okay, let's figure this out. So what is the minimum of 7 and 0? Between those two numbers, which one is the minimum? Well, obviously 0. 3, minimum of 2 and 5 is 2. Minimum of 4 and 1 is 1. Minimum of 1 and 4 is 1. Minimum of 3 and 2 is 2. Minimum of 13 and 0 is obviously 0. So these ones just become 1s, so those are gone. So all you're left with is 3 to the power of 2, 5 to the power of 1, 7 to the power of 1, 11 to the power of 2. This is the GCD of this guy. So that is why the motto for this question is think minimum. And this is, in my opinion, the best way of understanding greatest common divisor. Okay, now that you are an expert, we will begin the question. We are given this, okay? 205, 800, and 35k. I have to break those up into their prime factors. So that will become 205, 800. Get out your calculator. You can do this anywhere you want. It's 2 to the power of 3, 3 to the power of 1, 5 to the power of 2, and 7 to the power of 3. Okay, 35, I should say. 35k, well, that's obviously 5 to the power of 1, 7 to the power of 1, and then some k, and I don't know what k is. Okay, now, the only thing I'm told is k is less than 2940. All right, I think that will come into play later on in the question. Now, how do I go about this? I don't know what k is, but that's okay. I do know what is this side. This side is very helpful. We've got 2s, we've got 3s, we've got 5s, 7s. So I don't know what k is, but I am confident that it probably, although not guaranteed, is going to have at least some of those prime factors. Okay, so I'll say it's 2 to the power of something, A, 3 to the power of something, B, 5 to the power of something, C, 7 to the power of something, D, and then maybe some other stuff. All right, it can also include some other numbers, but I will talk a little bit about that later. But let's just make it simple for now. Let's just say the k is something like that. Now, if there is an additional factor, like let's say there was an 11 to the power of e, it really wouldn't change our GCD because here there is no 11. Here the 11 is 0. So just like in the primer, the minimum of 0 and e is 0. So the GCD wouldn't change no matter what you tag on to that k. The only thing we have to worry about later on in the question is ensuring that k is less than 2940. Okay, so let's keep it simple for now. Let's just say that's k. Some power of 2, 3, 5, and 7. All right. Now we have to figure out the GCD. So just as before, the GCD will be 2 to the power of the minimum of 3 and a. 3 to the power of the minimum of 1 and b. 5 to the power of the minimum of, here you have to be careful. This one's easy too, but here it's not c. There's a 1 here, so we got to combine that. So it's 1 plus c, right? Because 5 to the power of 1, 5 to the power of c, you would have to combine those exponents, and it would become 5 to the power of 1 plus c. So that becomes 1 plus c. And then finally, 7 to the power of the minimum of this 3, and again, 1 plus d. So 1 plus d. Okay, so far we're doing great. Now we have to think about this. We want this GCD to be a perfect square. So how can this be a perfect square? The only way a number is a perfect square is if the exponents are even. So that is something that we have to concentrate on. The exponents have to be even. It's the only way a number can be a perfect square. So that means that 2, or we don't even need to care about the 2. We can just talk about min of 3 and a. That has to be an even. So what are my even numbers? What are my choices? Well, maybe 0 or 2 or 4. But it can't be 4, right? Because the minimum of 3 in some number can never be greater than 3. No matter what you put in here, the maximum that I can have here is 3. So there's no reason to put in that 4. So 0 and 2 are my only options. And that means a is either 0 or a is 2. Plug it in and you'll see that works out. Now let's turn our attention to this guy. Minimum of 1 and b. It's got to be an even number, so 0, 2. Can it be 2? No. Because again, same story. If this is a 1, the minimum of 1 and b can never be greater than 1, right? If you put a 5 in here, the minimum is always going to be 1. The only way it can be less than 1 if b is 0. So that means b is 0. It's the only choice for b. And then now we go to the next one here. The minimum of 2 and 1 plus c. What can that be? Well, our choices are 0 and 2 and 4, right? Even numbers. But you can't have a 0 because the only way to get a 0 is for this to be -1. And if that was -1, then k would no longer be an integer. Remember, this was k, right? If c is -1, we'd have a 5 in the denominator, and that's not going to make k an integer. So c can only be 1 in terms of the smallest value for c. If c is 1, then the minimum would be 2. And that's the only way we can make the minimum. But c could also be something bigger than 1. It wouldn't change the minimum. For example, if c was 2, this would be 2 and 3, and the minimum would still be 2. So c could have a few choices. I'm not sure how many, so I'll just put 1, 2, ... We'll have to figure that out a little bit later. And then now, same story here. The minimum of 3 and 1 plus d. Well, remember, we have choices 0, 2, 4, like that. Can it be 0? Cannot be 0, because the only way that could be 0 is if d is -1. But we can't put d equals -1, because that would make k a non-integer. So d has to be at least, could be 0, but if it's 0, then the minimum would be 1. But we don't want 1 because 1 is not an even number. So 2, I think, is the only option. And that happens when d is equal to 1. And the minimum can never be 4, because the minimum cannot be greater than 3. All right, so these are our options. So we have boiled it down to this. So that means my A has 2 choices, 0 and 2. B is only 0, D is only 1, and C is what I have to kind of think about. All right, so here we go. Let's first talk about A equals 0, and then we'll talk about A equals 2. When A is 0, my K was 2 to the power of A, 3 to the power of B, 5 to the power of C, and 7 to the power of D, right? So when A is 0, it becomes 2 to the power of 0, 3 to the power of, well, B is always 0, 5 to the power of C, and 7 to the power of 1, because D is always 1. So this conveniently, very nicely actually, breaks down into just 5 to the power of C times 7. Okay, great. And recall that K has to be less than 2940. So 5 to the power of C times 7 has to be less than or equal to 2940. Divide through by 7, and that means you get 2940 divided by 7 is 420. So 5 to the power of C has to be less than 420. The only way that's possible is if C is 1, 2, or 3. If C is 4, it would become 625, and that is not less than or equal to 420. Okay, so we got some values for C when A is 0. Let's do the exact same thing for A is 2. When A is 2, my K becomes 2 to the power of 2, 3 to the power of 0, 5 to the power of C, 7 to the power of 1. So this is 4 times 5 to the power of C times 7, and that has got to be less than or equal to 2940, just like before. So divide both sides by 4 and 7, and when you do, you get 105. And therefore here, the only possible choices for C are 1 and 2. If C was 3, it'd be 125, and 125 is not less than 105. All right, great. I've basically done it. I've got pretty much all the values for each scenario. I've got, let's see here, when C is 1, K would be 5 to the power of 1 times 7, right? Because that's what K is, and that's 35. When C is 2, it would be 5 to the power of 2 times 7, which is 175. And when C is 3, it would be 5 to the power of 3 times 7, which is 875. All right, great. Over here, K is, this was K, right? Yeah, so 4 times 5 to the power of 1 times 7, and that is 140. And when C is 2, K would be 4 times 5 to the power of 2 times 7, and that is 700. So there we go. I got 1, 2, 3, 4, 5. 5 values for K. Or did I get 5? Yeah, I got 5. Okay, great. That should be the answer, right? Let's see. Oh, these are way more than 5. My answer is 5, but these numbers are so much more. So what did I miss? Well, it had to do something with the fact that k could have some extra prime factors attached to it. I touched on that a little bit earlier in the question, but I didn't want to bog you down too much. And that is why there's so many more than what I found. I found 5, but there's a lot more because they're tagging on extra primes. And if you tag on an extra prime, the GCD doesn't change because there is no 11 here. So the min, and I think I touched on this a little bit, the min of 0 and 1 is still 0. So when you tack on prime numbers to k, it wouldn't change the GCD. Now you say, well, then there must be infinite. No, because k has a restriction. It's got to be less than 2940. Okay, so now we got to figure this out. How many more? All right. So let's just look at these 5. 1, 2, 3, 4, 5, and figure them out one at a time. I'm going to start over here with this guy, 140. 140 multiplied by some prime number can also be another k, as long as it's less than 2940. Okay, well, what are my prime numbers? I'll list them over here. In particular, remember all the primes greater than 7, because we've already done the 3, the 5, the 2, 3, 5, and 7. So those primes are 11, 13, 17, 19, 23, and so on, right? All right, so I want to add on another prime here. Well, when I do that, I have to ensure that k is less than or equal to 2940. And I can do that with an 11. Just get out your calculator, and you'll see that will be less than 2940. It actually works out to 1540. So that's valid. And all I did was that I added on another prime number to my established value of k. This new k will also work because it will not change the GCD. The GCD will still end up being the same, which is a perfect square, according to the big long explanation I did earlier. Okay, let's keep this going here. How about, can I add another one? Can I add 13? That's the next prime. And if I do, I get 1820. Great, another k. Can I put in the next prime, which is 140 times 17? And that is 2380. Great, that's also less than that. And then let's see if I keep going here and add 19. That will be 2660. And then once I get up to 23, it exceeds the boundary. So these are the only ones. So 1, 2, 3, 4. I got an additional 4. All right, great. So far I have 1, 2, 3, 4, 5, and then an additional 4, which is 9. Now, if I go back and look at the answer choices, I'm still way short. So there's a lot more. Okay, so that must mean all those come from these guys here. Okay, let's start. Let's start with this guy here. 875 is k, right? So can I add on another prime number and still make it 2940, less than 2940? And the answer is no, because if I choose the smallest one, which is 11, it'll exceed 2940. So that's not going to give me any new ones. Okay, no problem. I'm done with this one. I don't need to worry about that anymore. How about 175, the next one? Can I put anything in there to make it less than 2940? I think so. How about 11? If I put 11, then that's going to work. And then I think I can also do it for 13. Yeah. Because if you take 2940 and divide by 175, it gives you about 16. So basically that means that this number has to be less than 16. And of the primes, the only primes that we have in that list that are less than 16 are 11 and 13. Okay, so I got 2 more. I got 1 here and 1 there. All right, so I'm still quite a bit short of those answer choices that are hovering around the high 20s. Because so far I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 so far. Okay, well, I'm confident that a lot of them will come from the very last part, which is this guy right here. So we're done with 175. Let's move to 35. Now we have 35. 35 times some prime number has got to be less than 2940. Okay? Well, let's call that prime number P. P's got to be less than 2940 divided by 35. Correct? And if you do that math, P's got to be less than or equal to 84. So that prime number that I put in there has to be less than 84. Well, all of these prime numbers here that I listed are less than 84. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 additional K's. And that pretty much is what brings us up to that level of the answer choices. So let's add this up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then these 19, 11 plus 19 is 30. So 30 is the answer to this excellent question, number 25. That would be choice D.